Welcome back to ECE 501B. Homework number 4 is due next Friday, I think is the 19th. And today what I would like to do is finish up chapter 5, which is dealing with eigenvalues and eigenvectors. And then in chapter 6, I believe we start talking about inner products, which is an interesting way of looking at, dot product, or looking at combining two vectors, what we can tell by comparing or forming the inner product of those two vectors. And that will allow us to think about orthogonality and computing what it means to have vectors that are orthogonal, and that allows us a lot of nice flexibility. Here we've been usually focused on linearly independent eigenvectors, and that allows us nice properties in terms of forming a basis. And today we're going to spend a lot of time talking about nice matrices, and nice matrices are really just matrices that have a lot of zeros in them. And one nice matrix that's about half zero, not quite, is an upper triangular matrix. And we'll look at an example of that. Then we will talk about some different propositions. One, we will actually sort of show or prove that this relationship between upper triangular matrices and invariant subspaces. Then we will just start sort of stating some of these actually quite important properties. One is, if you do have an upper triangular matrix, you can now, by inspection, see a lot or learn a lot from that matrix. And one thing that you can learn is that just by looking at the diagonal entries on that upper triangular, if they're all non-zero, then you can invert that matrix. That's proposition 530. 532 is that the eigenvalues of your operator are on the diagonal in an upper triangular matrix when we look at its matrix representation. We can also look at the case of when is a matrix representation of an operator even more specialized than upper triangular. When is it diagonalizable? When can we have the upper part and the lower part all zero? And that's in a case where we have distinct eigenvalues, that where n is the dimension, where we have n distinct eigenvalues, and n is equal to the dimension of the vector space V. Then you can put all of these together and you can say, oh, if we now have a matrix representation of a linear operator that's diagonalizable, that means that we can make our basis of eigenvectors, and we can do a direct sum decomposition of the vector space using those eigenvectors as our subspaces upon which to decompose or separate or break out this representation of a vector space V. Let's start then by looking at just an example. Here is the notation that we are using. If I have a matrix A and I say, okay, that's the matrix associated with a linear operator T, and I'm going to just go ahead and assume this set of basis vectors. I'm on R3. That's the linear operator, is a linear map on R3. And here I probably by default wouldn't have to provide that standard basis, but I'm doing it just to be establishing the notation that we're using throughout. If we need to show the basis vectors upon which this matrix representation is generated, then we would include those in this list of vectors following the symbol of the linear operator. So here we're just using our standard basis, and hopefully either after today or even now you understand how to find the eigenvalues of an upper triangular matrix. we'll state that, but right now we'll just say that in fact those eigenvalues are on the diagonal of an upper triangular. They're on the diagonal of a lower triangular. They're on the diagonal of a diagonal matrix. So those are all nice matrices, and the reason they're nice, one of the reasons, is because we can immediately find or identify the eigenvalues. In this case, we could actually show that we have the following pairs of eigenvalues and eigenvectors. Lambda sub 1 equal to 2, that's associated with the 1, 1 entry, and you would expect, if this is now an invariant subspace, that that eigenvector better not have any entries below the 1, 1 entry in that eigenvector, if it's going to be an invariant subspace of the matrix A. Meaning, you take A and apply that or operate with that on on W1, you better get back in W1 by the eigenvalue eigenvector and relationship, and in this case you do. You operate on W1 with A, and what do you obtain? A vector that has 2, 0, 0, a column vector that's 2, 0, 0, and that's actually 2 times the vector omega 1. You can also show that A W2 is equal to 4, or lambda sub 2 W2, and now the eigenvectors get a little bit more interesting because we have an upper triangular matrix. It's not diagonal. It's not going to be just an easy show or verification. We have to kind of do the math to actually verify that indeed A omega 2 is 4 omega 2. But omega sub 2, you can see, still has some pretty good structure to it. It has a hard 0 in the last element of that vector. And finally, lambda 3 is associated with the 3, 3 entry, and that eigenvalue is 5, and the eigenvector associated with it is 2, 3, 3. Now, that being said, you could show those relationships for A and the W's and the lambdas, but let's just look at the idea or the concept of invariance or invariant subspaces associated with a matrix. So let's just let's observe what happens when we have a vector v1, and let's say that that's actually going to just be one of the standard basis vectors in R3, and let's let v2 be the corresponding second standard basis, and v sub 3 the other. And let's just look now with that and see how the invariance property of operating on these vectors with the earlier matrix A, what that looks like. If we now look at A v1, and A again was 2, 3, minus 1 in the top row, 0, 4, 1 in the second row, and 0, 0, 5 in the third row. And now remember how we learned a strategy for multiplying a matrix with a vector. We can now look at that vector and say, oh, it's going to be easy to multiply by this vector because it's just pulling off what? It's just pulling off the first column of that A. So this is now going to yield 2, 0, 0, and that, I hope you can see, is in the span of v1. Some linear combination of that v1 vector, and yes, it is. It's actually 2 times that vector. What happens when we now operate on v2 with A? So now we have 2, 0, 0 for columns. Now I'm going in the other direction. For the second column it's 340, and in the third column it's minus 115. If we use the previous strategy, now we're just pulling off the middle column, the second column, and this is now 340. But I hope you can see that that's now in the span of the first two vectors that we were using. It's in the span of V1 and V2, and you can see that now we're having this nesting type property of subspaces. Now V2, anything in V2 is going to be in the span of just V1 and V2. Anything in V1 is just going to be in the span of V1. And I think you can anticipate what's going to happen when we now use A3 as an operator, use A as an operator on V3. We pull off the third column, and that's now in the span of all three of those original vectors, V1, V2, and V sub 3. Yes?
So is any vector in the span of V1, V2, V3 is an eigenvector of lambda equal 5?
So now is the question, I think, is any vector in the span of V1, V2, V3 an eigenvector for lambda 3 equal to 5? What's the answer to that? Can I just pull any, so basically V1, V2, V3 span all of V or R3, correct? So now you're saying, can I just pull any random vector out of R3 and claim that that's an eigenvector for lambda sub 3 equal to 5? That's not what I'm saying here, so don't be misled by that. I'm just saying that AV3, when I simply am pulling off the last column in an upper triangular matrix, essentially, I now have built up or have to use all of the vectors that span that space. But V3 was an arbitrary vector, so to speak, in that z direction, but we know from this what the eigenvector has to be for lambda sub 3 equal to 5. It has to be in the span of 2, 3, 3. Any linear combination of 2, 3, 3, you hit that with A, and that will stay in that 2, 3, 3 line, or in that vector. So we're not saying that V1, V2, V3, we can pull anything from there, from that span, and claim that that's an eigenvector. We are showing that there is sort of this nesting property of vectors when we have an upper triangular matrix. So the first one, because the first column only has one non-zero entry, its vector is neat or nice. The next column over has 2 non-zero entries. The next column, 3 non-zeros, and it just keeps sort of filling up the space. So let's look at what other results we can arrive at based on upper triangular matrices and sort of this understanding with this example. So let's look at upper triangular matrices in a little bit more detail. And remember why we're doing this. It's because we're saying, now I'm doing air quotes, upper triangular matrices are nice. That's why we're looking at them. But before we even do that, let's just make a quick note concerning the matrix representation of an operator. What property, if I say, oh, give me a matrix representation of an operator, what property do you maybe think of immediately in terms of a matrix? And yes, I wondered how many clues I needed to give you, but because it was sort of a vague question, but here I was hinting at what structure, maybe geometrical structure, do you envision when somebody says, oh, what's the matrix representation of an operator? We know an operator goes from one space back to itself. And that means that we have a square matrix, and we really only need to specify one basis to get this matrix representation. So only need to specify one basis when we're dealing with an operator. But we're probably looking for, in this case, a basis that gives us a nice representation, a nice matrix representation. So we're looking to find a good or nice or efficient basis for the system. And our claim is that a good basis is one where the matrix representation of the operator is simple. And now I can try to sort of define what I'm meaning by simple. Simple means lots of zeros. So simple, what I mean by that is lots of zeros. So we're trying to now find a basis that we can use to find a matrix representation of a linear operator that makes this matrix representation simple. That's the strategy for today, really. So now we've already looked at or found or arrived at results. So results we've already developed. Are sufficient to show that for a finite dimensional complex vector space, there's CVS again, but this is finite dimensional complex vector space, there is a basis where the matrix representation of the linear operator T is as follows. The matrix representation of T now looks like lambda 0, 0, zeros all below it, and then right now we don't know what's there. That's supposed to be a star or an asterisk. It's pretty ugly, so you can go get a telescope and look at a prettier star than what I can create, but that's what that is. So this just means that all of these entries we're not worried about. Those are arbitrary. That's what that ugly star means. But how can we already have the results to verify or to believe this, that we can find a basis of our vector space V, given a linear operator T, to put it into a matrix representation like this. So how do we verify that, or what's the thinking behind that? The proof is we had a theorem that says every operator on a finite dimensional complex vector space has a eigenvalue. So we previously proved that a linear operator T has at least one eigenvalue, lambda, and an associated eigenvector V. That was theorem 21 in chapter 5, that we can find at least one eigenvalue for a linear operator on a finite dimensional complex vector space. Complex, that's key to have that C in there. So now we have an eigenvalue and an eigenvector. Well, now why don't we just make that our first basis vector in our list of basis vectors making up capital V? But how do we get the other basis vectors? Well, we know how to extend from one up to many. We have that result as well. So we already learned, so we can say that previously learned that one can always extend a linearly independent list of vectors on the finite dimensional complex vector space. That's not true in general. If I just give you a set of random basis vectors for a vector space V, what's the matrix representation look like? In general, what does the A matrix look like? The matrix representation of an operator T. Or what's the first column look like? Suppose I give you the fact that we're okay with that star. Those are arbitrary. We don't care about what happens on the other n-1 columns, but what's the first column look like? Or what do we do? We take the basis vector, the first basis vector, and operate on it with T and say, oh, how do I create that out of a linear combination of all of my basis vectors? So I take A11 times the first basis vector. A21 times the second, plus A31 times the third, etc., down to A sub n1. So those A's are how we those are the scalars that we use to combine our basis vectors to create the representation that T, let's say V1, creates. In our case, what do we have? We actually have an eigenvalue and its associated eigenvector V. So that now if we put TV in the first column of our matrix representation, and then we extended that basis up to T, let's say Wn minus 1, that's now going to be V W1 W to the n minus 1. And in general, if we just did the general, this is how we get that A11, A21, A sub n1. It's just a linear combination of the V and the other basis vectors. And this would be A12, A22, AN2, and we just keep going. So this is for a general matrix representation A. For our case, what do we know? Well, we know V is an eigenvector that has as its eigenvalue lambda. And now we can basically clean or create a much nicer or a simpler A matrix representation. So for our case, we actually have A equaling the matrix representation of T. What's in our first column? That's just lambda, and then we have zeros weighting or scaling all of the other vectors, because V is an eigenvector of the linear operator T. And then over here, we don't care, and we don't care here either. But we definitely have that structure that we were after. And we could, if this is not making any sense, let's just remember, in general, the jth column of this representation is the result of applying T, the linear operator, to the jth basis vector. So our matrix representation is now, how do we combine these basis vectors to create T V sub j, for example, or the jth column? Our first basis vector in fact is the eigenvector V, and has the following representation. in terms of the basis vectors. If I now say, oh, let's write v in terms of the basis vectors, I have 1 times v plus 0 times w1 plus 0 times w2, etc., 0 times w sub n minus 1. And these are all the basis vectors. And that's why I can now have that lambda with zeros everywhere below it. And TV is equal to lambda v for v being an eigenvector. In other words, or that is, the A11 in our matrix is just lambda, and the let's say L1s are all equal to 0 for all the other L's. L equal 2, 3, up to n minus 1. Actually n, isn't it, in this case? No. I was using n before, so let me just say n. So there's our sketch of the proof of why we can write a matrix representation as lambda in the first column with everything below it zeros. But that doesn't look very upper triangular, does it? So we can do a lot better than that. But we can do even better than the above. And in particular, with an upper triangular matrix, is what we're shooting for, and is one where all of the elements below the diagonal are 0. And that we've already been using in our examples. So now we are really looking at lambda 1, lambda 2, lambda sub n, and there's a star, but everything else are zeros. That's our upper triangular matrix, and we've seen that we can produce the first column. Now we're going to basically learn that we can produce this upper triangular matrix structure. So now this is the next proposition, proposition 26, and it goes as follows. If T is a linear operator on a vector space V, and we have the following vectors v1 through vn as our basis, on our vector space V, then we can consider the following three statements to be equivalent. A, the matrix representation of T, and let me just go ahead and be explicit with V1, V2 up to V sub n. Let me just say that that is upper triangular. And I may, for notation purposes, just say UT. So now the matrix representation, let's just assume that the matrix representation with this set of basis vectors is upper triangular. That we know. Well, that's equivalent to saying the following, that T V sub L is in the span of V sub 1, V sub 2, up to V sub L for each L up to n. There's that nesting property that we've talked about. So if we have an upper triangular matrix, then you give me one of those basis vectors, then if I operate on it by the linear operator, then the result of that is going to be in the span of that basis vector and all preceding basis vectors. The other equivalent statement is that the span of V1, V2 up to V sub L is invariant under the linear operator T for each L equal to 1, 2, on up to n. So that says that you give me V1, the first basis vector, then that's going to be an invariant direction. You give me the second basis vector, or the first two basis vectors, then those two are going to contain anything, any vector, any output from T operating on the span of any vector from V1, V2, etc. So how do we show that or demonstrate that or prove that? First part, let's show that A is equivalent to B. Statement A and B are equivalent. And equivalence, we're going to go through this. In the book, I think they basically say it's obvious that this is true. That's their proof. So let's now just kind of step through or discuss that and show that in part one, we're going to show that A is equivalent to B. And then in part two of the proof, we'll show that B is equivalent to C. And that basically covers our base. So now let's look at A being equivalent to B, and that means that we need to show what? Implication in both directions. So let's look at A implies B. So let's look at A implies B. And what was A? A was we have this matrix representation that's upper triangular, and B is that we have this nesting of basis vectors in terms of the span. So now we have a upper triangular matrix representation of T. What's the nth column of that matrix representation look like? Do you see what that looks like? The nth column of the matrix representation of T is the expression of T V sub L in terms of the basis vectors V1, V2, V sub n. That's the definition of the matrix representation. the nth column of an upper triangular matrix has a specific structure. And what does that structure look like? So the nth column of an upper triangular matrix looks like, here's the column. This is the nth column of the matrix representation of T. Can we subdivide that or break it into two pieces if it's upper triangular and it's the nth column? Now we know that everything below the diagonal is 0, don't we? So this is now, how many elements do we have here? We're not going to even say what those are, but how many of these do we have? How many rows? So now this is the nth column. So now we walk over L steps, and what do we know? Well, it's a square matrix, and now we go down. How far do we go down before we get to a 0 entry? L. So we need to have the diagonals non-zero. So this is now L elements. And below that, we have n minus L elements. So that's now equal to this A1L, A2L, A sub LL, 0, 0. And that's what T v sub L looks like. Or that says that we now have A1L times V1 plus A2L times V2 plus A sub LL V sub L plus 0 times V sub L plus 1, etc., 0 times V sub n. But what does that say this T v sub L is expressible as? A linear combination of V1, V2 up to V sub L. And that's statement B. So this means that T v sub L is expressible in terms of only V1, V2, V sub L. Or that now says that T v sub L is an element of the span of V1, V2 up to V sub L. And that's true for any L. So now we've shown that A implies statement B. That was statement B. So let's now show that B, statement B, implies statement A. So statement B says that we have TV1 looking like what? What does that belong to? Or what's it an element of? Based on statement B. Statement B said that TV1 would be an element of span of V1. TV2 is span of V1, V2, etc. So that's what we're going to just state. This is now B. So if TV1, that's going to be in the span of V1. TV2 is now the span of V1, V2, and this is that nesting that we illustrated at the top of the hour, the top of the show, however you want to refer to it. So this is now saying that T V of L is now an element of the span of V1, V2, V sub L. Then if we wanted to, we could say, oh, that means that if I had a TV1, that's some scalar multiple of V1. And TV2 is what? That's some scalar multiple of V1 and V sub 2. And TV3 and we can just keep going. So that now if we go all the way down to TV sub L, that's some linear combination of V1, V2, all the way to V sub L. But now I can use those scalars to populate a matrix. And I've hopefully indexed those appropriately, so that now I have the matrix representation of T is now alpha 1, 1, and nothing else below it, alpha 1, 2, alpha 2, 2, and nothing below that, alpha 1, 3, alpha 2, 3, alpha 3, 3, etc. down to alpha sub n n. And here is alpha 1 n, alpha 2 n, and there's my matrix representation of T. And what is that by definition? Upper triangular. So now we've shown then, so this now shows that the matrix representation of T is upper triangular. And we've shown that B, statement B, implies statement A. And now we've gone in both directions. So now we've shown the equivalent of A and B. And that's part one of our two-part proof of this showing equivalence of the three statements. So now, part two is B if and only if C for statements. And let's just show that C implies B. And just to do it a little bit different, let's do this by a contrapositive strategy, so that we can start looking in all sorts of different ways. So now if we're using the contrapositive strategy for showing that C implies B, what does that really mean? That we're assuming what statement implies what other statement. So now we're saying we're going to assume not B. I don't know why I'm changing up all my cases. So there, let's assume not B and show not B implies what? Not C. So if you really wanted to get dizzy, you would just start doing this, right? I'm saying B implies C, but I'm going to do it. No, I said C implies B by showing not B implies not C. Right? That's what I'm doing. So what's not B? What's not to be? To be or not to be. So now we're starting with the not to be. What's not be? So T V sub L is not in the span of V1, V2 up to V sub L. That's not B. So if T V sub L is not an element of the span of V1, V2 up to V sub L, that's not B, and that's true for each L. Then the span of V1, V2, V sub L can't be invariant. If we're saying TV sub L is not in V1 through V sub L, then TV sub L is not in that original list of vectors, so it's not invariant. We're not going back to where we sort of came from. So now this span can't be invariant because T acting on a vector in that span of V1 through V sub L produces a vector not in that span. And that's what we were trying to show. That was not C. What was C? I've completely forgotten. C talks about being an invariant subspace. So this, we just showed that it's not an invariant subspace, and so we showed that assuming not B implies, assuming not B implies not C. Very simple to show. C implies B, right? All right, so now we need to show just the opposite, or the other direction, which is to show that B, statement B, implies statement C. Now we are assuming statement B. If B, then C is true by the definition of invariance. In other words, TV1 is in the span of V1. That's statement B. TV2 is in the span of V1, V2. And we can just keep going. TV sub L is an element of the span of V1, V2, V sub L. In other words, V1, V2, that list up to V sub L is invariant under the T operation. Is T invariant? Or statement B indeed does imply statement C, and now we've shown that B, if and only C, and now we can draw our box to say that we're done. We showed A implies B, or A if and only if B. Now we've shown B if and only if C, and we've chased our tail. We've completed that set of demonstrations. Let's now look at some statements about upper triangular matrices. and we're not going to spend time showing those. Let's just refer to the textbook for their proof. Theorem 27 in Chapter 5. Given a vector space V, a complex vector space, and now it's pretty important to make sure that we're distinguishing when we're assuming complex or when we're assuming real. We can do a lot more actually assuming a complex vector space. And T, a linear operator on that vector space. Then there is a basis of V of that vector space V where the matrix representation of that linear operator has an upper triangular form. So you give me a linear map on a complex vector space, finite dimensional, and I can find a set of basis vectors that will give me a matrix representation of that linear map that's upper triangular. That's not necessarily true for real vector spaces. I can't upper triangularize a generic linear operator on real vector spaces, whereas in a complex vector space I can. So let me just say that this is not necessarily true when we're working with real vector spaces. So let's just sort of discuss our way around that notion. Think about the form of the matrix representation of an upper triangular matrix. So here we have the matrix representation of T, and I'm already giving away some of our subsequent statements by labeling those as lambdas. But there's our upper triangular representation. The fact that the first column has only one non-zero element means that the first vector of our set of basis vectors is what? If I'm forcing that first column to just have one non-zero entry on the diagonal, what's that telling me about my first basis vector in this list of basis vectors that I'm using to make this matrix representation? It has to be an eigenvector, right? So now this first vector of the basis is an eigenvector. And you know what it looks like. It's 1 with zeros below it. So we have an eigenvector of T, and it has an eigenvalue lambda 1 based on how I defined my matrix representation, which I said lambda 1, lambda 2, lambda sub n. I know that's true. But what do I know about if I'm working, and then I can just keep sort of going with that idea. Just keep using eigenvectors as basis vectors. But what if I had a linear operator on a real vector space? What have we shown? I don't know that it was the last time that we were together, but what have we shown about some linear operators relative to the existence of eigenvalues on a real vector space? Are we guaranteed to always have an eigenvalue for a linear map on a real, over a real field, or the field of reals? And now we looked at that rotation, didn't we? So a rotation doesn't have an eigenvalue. So now we could say, but if this linear operator t has no eigenvalues, which we know we can generate cases that satisfy this condition. So if t has no eigenvalues, and that's possible, over the set of reals, then we can't put that very first column in place in this upper triangular form. So we can't create an upper triangular matrix when we're dealing with the generic real vector space, or a generic vector space that's real. Then it must follow that the linear map T has no upper triangular form. So there's the power or the beauty of having FD CVS versus FD RVS.
Can we apply the same theorems for lower triangle or just upper?
So now the question was, could we do this for lower triangular? It's just, I think it's cleaner to see the invariance property with upper triangular. So if you can do it, I'm not so no, I don't think you really get this invariance property that we are creating with lower triangular. But you can look at that and see if you can come up with examples that illustrate that or don't. So now let's state some other propositions. Proposition 30. If we have a linear operator on a vector space V, and that linear operator has an upper triangular matrix representation, then this linear operator T is invertible if and only if all the diagonal entries of this upper triangular matrix are non-zero. So now if we want to, by inspection, see if this matrix, if this linear map is invertible, then if we find a matrix representation in which all of the diagonal entries are non-zero, boom, we can make that claim. Now, this particular proposition Proposition 530 that we just wrote down leads to one of the key concepts or results in this chapter. And that's Proposition 32, which says, given a linear operator T, which has an upper triangular representation on some basis, that's what we're assuming. So now we're given this linear operator which has an upper triangular representation on some basis. The eigenvalues, which, as I said, I've been giving that away all day, but the eigenvalues of this matrix representation of T are on the diagonal entries of the upper triangular matrix representation. So now we can show this different ways, but here's one way to think about it. Suppose we now take the following basis vectors, v1 through v sub n. Or, said another way, the matrix representation of T on that set of basis vectors, v1 through v sub n, is now upper triangular. Let's now take a scalar variable lambda in our field. And let's look now at the matrix representation of the operator T minus lambda I over that same basis. That now takes each of these diagonals and compares it with lambda. T1 minus lambda. I'm sorry, lambda 1 minus lambda, lambda 2 minus lambda, etc. Lambda sub n minus lambda. Here we're not worrying about that, but that preserves the 0. So this is now the matrix representation of this new operator T minus lambda I. And what do we know about the eigensolutions of that linear operator? Eigensolutions are associated with the null space of T minus lambda I. So now we want, for our eigenvectors, they need to be in the null space of T minus lambda I. which means we want t minus lambda I to be injective or non-injective if we want it to have a non-trivial null space. So it now needs to be non-injective. If it wasn't, we would have the trivial null space, which is the 0 vector. And we want our eigenvectors to be non-zero. So otherwise, null space is trivial. But now if we have a non-injective map, what else do we know? Remember, for an operator, this relationship of equivalence between something being injective, surjective, and invertible. So now also remember that for operators, injective, if and only if surjective, if and only if invertible. And now we have this non-injective map. So this is equivalent to saying we want t minus lambda sub I to be non-invertible in order to make it non-injective for some value of lambda. And our previous result Proposition 30 in Chapter 5 shows that upper triangular matrices are invertible when if and only if, what do we need on the diagonal? We want those diagonal entries to all be non-zero. So our previous result shows that upper triangular matrices are invertible if and only if we have non-zero elements on the diagonal. So if we want to make this matrix non-invertible, and we have a structure like this, with lambda 1 minus lambda, lambda 2 minus lambda, lambda n minus lambda, what can we say about lambda if we want to make that non-invertible? We want to zero out one of those entries. Do we not? We want to make it 0. Then it wouldn't be invertible, that matrix. So thus, lambda equal to lambda 1, lambda equal to lambda 2, all the way up to lambda equal to lambda sub n are all the values that make this operator t minus lambda I non-invertible, and hence all of those values of lambda are the eigenvalues of that operator, and hence are the eigenvalues of our map T. And that's what we were wanting to show. That the diagonal contains the eigenvalues of that linear map. The diagonal entries of an upper triangular matrix. So we can look at, or if you finish up chapter 5, it talks about diagonal matrices, not just elements on the diagonal, but now diagonal matrices, and it has a few results or propositions about real vector spaces. I'll write those down just in notation, but you can study those on your own. And we'll pick up with chapter 6 the next time we're together.